So this morning, I think we were going to have the perfect researcher to introduce you all to reinforcement learning. So this morning, we're going to have Adam White, who's an assistant professor at University of Alberta, and he completed his PhD in 2015 with Richard Sutton. His thesis was had to do a lot with the general value functions, which I think he's going to tell you about. But the title exactly of his thesis was Developing a Predictive Approach to Knowledge. One of the really cool things I like about Adam's research is that he's one of the few researchers who really pushes reinforcement learning techniques on real robots. So he's one of the first person that I've seen deploying these algorithms and trying them out on real robots. And I really hope that he's going to be able to show us maybe some videos of the famous CritterBot that he worked on during his PhD thesis. Adam is also a senior research scientist at DeepMind Alberta. And he's also been recently leading a Coursera specialization on reinforcement learning along with Martha White. And I believe that you can also find this reinforcement learning course on Coursera right now. So, so let me introduce you to Adam now.
Hello, everyone. Okay, so I guess I should get going. I just have to share my screen. And let's get going. All right. Okay, so today is going to be all about reinforcement learning. So as Pierre-Luc said, I have a bunch of affiliations, the RLI lab at the University of Alberta, the Alberta Machine Intelligence Institute, AMI, and of course, DeepMind. So I was looking at the Slack channel, I saw all these people posting really nice pictures of nature and grass and stuff, and I really, really liked it. So I thought I would just take a second just to kind of, make it seem like I'm a person, not just this talking video on the screen. So, I'm from Edmonton, Alberta. That's the first picture in the top left. Believe it or not, we actually get summer here, and it actually can be pretty sometimes. But I'm originally from New Brunswick, which is on the east coast of Canada. So it's right beside Maine in the US, if you know where that is. That's the picture with the bridge on the right-hand side of the screen. And I also want to tell you a couple of things that I like to do. So this is a picture of two people doing a funny sport called Gaelic football that for strange sequence of reasons, I like to play that sport. And I'm also a really big fan of nature. I spend a lot of time outdoors. I spend a lot of time looking at animals. And this is a picture of a buffalo at Elk Island National Park, which is about 45 minutes from where I live, and it's just my favorite place on earth. So my job today is to get you guys into reinforcement learning. You spent the last couple days learning about supervised learning methods and about deep learning, and of course, deep learning is very much coming together with reinforcement learning, but reinforcement learning is its special thing and deserves its own introduction. And so we're really going to get into that today. So what is reinforcement learning? Reinforcement learning is agent-oriented learning, right? It's learning by interacting with the environment to achieve a goal. This really is about a platform where the agent has to, take actions and collect its own training data and then learn things from that training data, and ideally learn how to collect better data over time. So it's all about trial and error learning and delayed feedback. So this is a really big theme in reinforcement learning. You get rewards for things you do, but those rewards might come much, much later. So you have to learn what to do to achieve those long-term goals. And so we like to say that it's the kind of machine learning that's most like animal learning. It really was inspired by people like Andy Bartow and Rich Sutton looking at what was happening in the psychology literature, looking at the animal learning literature and saying, there's something missing here. We can do something better. And that thing better was also something that was useful for, artificial intelligence and robots. And the key thing is that the system learns for itself what's right or what's wrong. So we don't need a human in the loop to tell the agent that was a good action, that was a bad action. Now, of course, we can use that, but the primary idea is that the learning system is completely autonomous. So what's going to happen today? Well, I'm going to just introduce you to the basics, right? I'm going to get you into reinforcement learning and sequential decision making so that you're ready for the advanced topics, which are going to come fast and thick over the next hours and days. So the basics, I mean, we're going to talk about states, actions, rewards, time, MDPs, policies, and value. These are like the key constructs of reinforcement learning. And we're going to get into the most well-known algorithm reinforcement learning, Q-learning. And of course, we're going to talk about function approximation because we want to scale our systems up. We want to handle real problems. And of course, I won't be able to hold myself back throughout. I'll make comments about open challenges and things that are about doing learning in the real world and probably give some advice. But so I just wanted to set the expectation. So I said it was planting seeds. And what I mean by that is, of course, you're going to hear about a lot of very advanced topics. You're going to hear about meta learning and model-based reinforcement learning and off-policy learning. And you really need to know the fundamentals to appreciate those things properly. So this lecture is going to be targeted at people with absolutely no background in reinforcement learning. It's what I did at the summer school last year, and it worked out really, really well because, you know, we need to get into the basics and the fundamentals before we can understand other things. So there's some prereqs, some basic knowledge of stats and probabilities and calculus, but nothing too heavy. But you may be sitting there thinking, well, you know, I've read some blogs and I've implemented Q-learning, I've implemented DQN and all these other things. So maybe I don't need this. And my response is, you know, improving your understanding of the fundamentals of formalism, of the proper terminology is always a good investment. And time after time, I see projects or review papers where it's clear that people didn't have a full grasp of the fundamentals and their projects and their ideas were very limited. So this is always time well spent. And of course, I have to do a bit of myth busting because there's a lot of memes out there. There's a lot of false truths about reinforcement learning across blogs, across different posts on the internet. And I'm trying to give you a sense of what the real fundamentals are here. So there's obviously many ways to learn about reinforcement learning, and I'm just going to scratch the surface today. So what the best place to learn about reinforcement learning is this book. It's the second edition of the book that I read a long time ago in Rich's class. It's beautiful, it's well written, the examples are brilliant. It takes a long time to get through because it's huge now, but it's a really good idea. But to help you with this, like Pierre-Luc mentioned, Martha and I made a 4-course specialization on Coursera, so you can follow the link there to get to it. It really goes through the basics, starting at bandits, all the way to deep learning and policy gradient and average reward, and even finishes with a capstone project where you implement a deep learning system. And so I can't make a better set of lectures than this. Every one of those lectures was filmed and refilmed, and we had scripts and lots of editing. So if you want to see the best that I can possibly do, it's represented in that specialization. But today I'm going to do a little bit of something different where I'm going to try to give you a high-level overview of the basic ideas. So I think the right way to organize reinforcement learning is to think about, you know, what are the key attributes of reinforcement learning? And it's especially useful to kind of contrast these perhaps with what you've learned so far in the summer school. So for me, the big things in reinforcement learning are evaluative feedback. So, you know, you're going to get reward, and reward is not an instruction. It doesn't tell you what to do. It just gives you an idea of the goodness or badness of the action the agent just took. And like I mentioned, we're going to really care about delayed consequences. So, you know, you play a game of Go, you make a sequence of moves, but you only find out at the end if you actually won or not. That's a big part of the reinforcement formalism. And this will be one of these myths I bust as I go along. You have to associate different actions with different situations, right? It's not just about finding one good action that works in all situations. You know, if I go walk down the street, I walk a certain way. If I go walk along the beach, the sand is very different. I have to walk a different way in sand. So we have to associate different actions, different situations. And of course, a really big one for me, online and incremental learning. We want to learn as the system is interacting with the world. So the agent takes an action, the world responds, and then the agent tries to do an update, tries to learn something from what just happened so it can do a better thing on the next step. So always learning as the system is running. And just like animals and people, you know, sometimes the best way to understand things is to do trial and error learning, to try things out, see what happens. But we also have to worry about, you know, balancing this exploration-exploitation trade-off that I'll talk a bit about. And the last one's non-stationarity. Non-stationarity is really a key aspect for me because it's what the world is really like. The world is not a fixed game that always stays the same. And if you just learn how to play the game perfectly, you can do that forever. The world changes over time, right? The seasons change, my body changes. If I have a robot, the tires on that robot deflate, and so it drives differently. Changing is just a natural part of life, and our learning systems should be robust too. So these are, for me, the hallmarks of reinforcement learning, and we'll start with this evaluative feedback thing, and we're going to do it through a game. So I'm going to pretend like COVID isn't happening, and I'm just there in the room with you guys, and I'm going to get you to play a game, and Pierre-Luc is going to help me play this game. And so what happens here is that we have 3 choices, and whenever we click one of these choices, we're going to get a number. And what we want to do is we want to click the button that gets the best reward on average. We just want to find one button. It's going to be 1, 2, or 3. And then once we figure out it's the best, we'll click it forever. So in chat, I want you just to tell a button that you think is best that we should pick. And Pierre-Luc will just pick the first one he sees. And he'll tell me, hopefully.
3.
Okay, 3. So we got a reward of 12. Now what? Another one?
Let's go.
Say again? 2. Okay, now let's maybe do 1. So we get 12, 22, and 3. So I'm thinking most people will want to do button 2. We got 22. Got 21. That's pretty good. Maybe I'll click it again. 24. That's really, really good. So I've got like 22, 21, 24, and the other ones were lower. 23. Now at this point, I should probably try another button because maybe I was just unlucky when I checked them.
Someone said you should press 2 a lot. Lots of exclamation marks.
Well, I just got 22 and another 22, so now it's really unclear. But I haven't picked 3 in a while, so I'm going to try 3. That one's pretty low. So this gives a 3. Now that's pretty bad. So maybe you guys are right. Let's see what the answer was. The best one was 2, so you guys are totally right. So now I can scroll down, hopefully. Yeah, and so it's the same game again. I'm just going to play it, and I want you guys to think of the action choices. So I'm going to follow a basic strategy here. So I get an 8, get 15, get a 9, get 15 again, get an 8, and I get a 9. They're all seemingly similar. But if I look at the distributions, and let's just look at this line here, the expected reward, this last one has a really good expected reward, 33.31. And that's because a small percentage of the time it gives 196. Now, I wouldn't have seen that unless I clicked it a lot, because if I keep clicking it, I'm going to get a lot of 9s. Once in a while, I'll get a 196, right? So I wouldn't have thought that that was a big one. Okay, so this was a multi-arm bandit problem. I can just close this thing and go right back to the presentation. And so what I want you guys to think about while you're sitting there is, how did you decide which arm you wanted me to select? How were you keeping track of the rewards that you saw? Were you just keeping them in your memory? Were you trying to do something else? How many polls do you think I would need to decide which arm was the best? So, you know, you were forced to balance getting reward now with figuring out which arm was the best. And that was really strongly illustrated with that second example where we had the one arm that most of the time gave 9, but every once in a while gave that huge number. This is indeed life of a reinforcement learning agent. And so that was a bandit problem. And in a bandit problem, all we care about is picking the arm that gives the most rewards. So we're just looking for the best arm, and once we figure out which one's the best, we'll pull it forever. But as you saw, there was distributions under the hood, so we had to select all the arms a lot to make sure that we had a good estimate of their average reward. And so the bandit problem shares a lot of the characteristics with reinforcement learning. It's evaluative feedback. We want to figure out how things are working online and incrementally. We need to do this trial and error thing, right? I needed to try all the buttons because I could just get lucky and pick a good one, but maybe I get unlucky and I get stuck on a bad button. And how could I make it non-stationary? Well, to make it non-stationary, you could just have those distributions either slowly change over time, or maybe every 1,000 polls, the distributions completely change. And then I have to figure out how to adapt to the new version of the problem. So it shares a lot of the characteristics of reinforcement learning, and that's usually why we start there. That's why the textbook starts there. And that's why it's a good way to get you thinking about reinforcement learning, you know, before you get into the heavy stuff of MDPs and all the other stuff that follows. So there's going to be a whole lecture on this this week, and so look forward to that. But let's see now how that differs from the reinforcement learning formulas, and then we're going to use the rest of the talk. So this is the basic setup of reinforcement learning. You have an agent, it interacts with the environment. Okay, so the agent is the decision-making part, it's the learning part. It picks actions and it learns about the world, and the environment is all the rest. So they interact at discrete time steps. They take turns. The agent takes actions and then the environment responds. The agent takes actions, the environment responds. So the environment has some sort of state. And so in this case, the state is a configuration shown on the screen. The state is there's broccoli with a rabbit beside it, with a carrot beside that, and a tiger beside that. Okay, that's an example of a state. And then we can have an action. In this case, our action is going to be that we're going to move the bunny to the right. Okay, and that's going to result in a new state. And the new state is going to be that the bunny is over top of the carrot, it ate the carrot, and now the bunny is beside the tiger. Okay, so that's going to generate a reward. The reward is plus 10 because rabbits really, really like carrots. Carrots are great. And so we're going to use this notation. So the current state is called ST plus 1. So it's a member of this set of states. The reward is a real number. It's called RT plus 1. And the actions the agents take is AT. And it comes from some set of actions which may be different for each state. And so please note that the rabbit we took an action so that the rabbit was beside the carrot so it could eat it, but now it's in a new state where the rabbit is beside the tiger, and maybe the rabbit can't move away from the tiger, so that might lead to bad reward now. Now remember, the state is the full configuration. So in this case, the state is broccoli with nothing beside it, rabbit, tiger. The agent isn't the rabbit. This is just a configuration of the world. Okay? And so this is the basic time step of a reinforcement learning system. You have a state, you take an action, the world responds, the environment responds with a new state and a reward. Okay, and this just goes on and on and on forever. It produces a trajectory of experience. You start at some start state S0, take actions, get rewards, next states, on and on and on and on forever. And so just like the tiger example, you know, the actions have immediate rewards. We get the plus 10 for the carrot, but it affects the future states that we're in, and therefore the future rewards, because probably the rabbit isn't fast enough to escape the tiger, so we won't be able to move the rabbit away from the tiger, and the tiger will get the rabbit, and then we'll get a big negative reward. So there's long-term consequences to decisions. And so what are these MDPs, these Markov decision processes? Well, if the environment may be unknown, may be stochastic, could be complicated, the MDP formalism can express all kinds of environments like this, okay? So they can be huge, they can be messy, they can be confusing, and that's what MDPs are for. So a problem is a finite MDP if the set of states, actions, rewards are all finite. So it could be a huge set, could be really, really, really big, but it just has to be finite for each one of them. Of course, we can generalize this to countably infinite in other cases, but for our purposes today, finite is good enough. And there's going to be a transition function that describes the probabilities of how the world transitions from one state to the next and emits the reward. And we're going to have this requirement of the Markov property, which we'll discuss in a second. But first, let's start with this transition dynamics function. So in general, when we're in a state S, you know, we take an action and then many possible things could happen next. Okay, so we want to represent this dynamics because the outcomes could be stochastic. You could be in state S, the agent takes an action, and it could end up in state S prime on this term, but it could end up in a different S prime the next time you come back to that state. So it's stochastic. So we're going to use the language of probabilities to describe this process. So what we have is this transition dynamics function here. Okay, so the transition dynamics function P formalizes this notion. So P tells us the joint probability of the next state, S prime, and the reward, R. Okay, so this is a probability distribution. So it's expressing, you know, if I start in some state S and I take action A, what is the distribution over next possible states and rewards that I could get, which is visualized in this diagram here. There's many places you could end up. And so because this is a probability distribution, you know, we have to follow the usual rules. Things can't be negative and they have to sum to 1 in the appropriate ways. But this completely describes the dynamics of the agent's interaction with the world, because it says what happens when the agent does particular actions and states and what rewards it gets. Okay? So there's one extra piece of this, which is this probability only depends on the current state and action. Okay? So it doesn't matter where you've been. It doesn't matter what you did in the past. All that matters is the current state and the action you take for determining the next state and the next reward. And this is what we call the Markov property. And so what it means is that remembering earlier states won't improve your prediction, won't improve your control. Now, this is an assumption that we're building into our system. It makes the theory nice. It's something that we relax in practice, but it is an important thing to talk about. And we're going to get to an example about this and why this isn't maybe as limiting as you might think. So we have MDPs. We have transition dynamics that govern how the world works through probabilities. And now we want to talk about the goal of life. It's really simple. This is reinforced learning. So we just care about more reward. Okay? So the agent's objective is to maximize future total reward. That's an imprecise statement, but it captures the spirit of it. We care about all the reward we're going to see into the future, starting from right now when we take an action. And so how do we think about this? Well, we introduce this concept of a return. We call it GT. So it's saying on this time step T, the return is defined as the sum of future rewards. So the reward we would get by playing an action right now, and then the reward we would get on the next step, and the next step, and the next step, and so on, forever and ever and ever. Okay? So this is what we call the return, and I'm using, the definition notation so that's nice and clear. A dot over your equal signs means this is a definition. So what's the problem here? Yep.
If I just can interrupt, I think there was a question that someone was asking. Would you answer these questions live? I think it's related to the content you're presenting. So,
sure. Let's do one live and see how it goes.
Yeah. So maybe I wonder if Tolga wants to ask the question directly. I'm not too sure how I can unmute. Otherwise, I can. Okay. Yeah, we can hear you.
Thanks, Pierre. So my question was actually in regards to the diagram you showed, and that's like a quite popular one where the agent is interacting with the environment.
Yeah.
So the environment is stochastic and there's non-stationarity and everything, but I think in the real life situations, what we see is that humans or animals not only adapt to this dynamic environment, but they manipulate the environment, they shape it, they warp it. We build cities, we do agriculture, so we're kind of manipulating it. I was wondering, I mean, I know it's a naive approach to simplify the problem, but I was wondering if there's any attempt in kind of accounting for this manipulation in better defining the environment.
That's exactly what this formalism is saying. It's saying the agent can take actions. Those actions could be to blow up a building. Those actions could be to farm a field. Those actions could be to divert a river, and then it will change the state of the environment. So it's absolutely built into this framework that the agent can manipulate and change the environment.
Okay, thank you.
Great. Go through some animations here. Maybe it's a little recap for people anyway. Okay, so we talked about this return thing. It's caring about all the rewards in the future. I have a ... here, which means I'm possibly adding up an infinite number of things. Typically, when you add up an infinite number of things, you should worry that that thing might itself become infinite, and then our learning system is trying to optimize towards an infinite objective, so we don't want that. So what do? Well, we just add discounting. So discounting, we put it here in red, is just this gamma. It's a scalar quantity, and what it does is it just weights rewards in the far future less than immediate rewards. So the first reward here doesn't have a discount on it, so we get the full reward. But as we see further and further into this sum, the rewards are discounted with higher and higher powers of gamma. And so that just means kind of like economics, like $1 today is worth more to you than $1 in a year or 2 weeks or 2 years from now. So we're just saying we care less and less about rewards far into the future. And so as long as gamma is between 0 and 1 and the rewards are bounded, this will keep our return GT finite. And so what we want to do is we want to pick actions so that in each state, the agent should choose the action that results in the highest return in expectation. So we want to make GT as big as possible in every state, but we have to do it in expectation because just like the bandit problem, there's stochasticity. And so we have to do things in expectation, because if we just tried to optimize with direct quantities we saw without paying attention to the randomness, then we would get stuck. So we care about expectations all over the place in reinforced learning. Okay, so we've talked about evaluative feedback. We've talked about delayed consequences. It suggests this need, this MDP formalism suggests this need to associate actions with different states. And so let's talk about the key technologies for doing that. So the first one is policies, right? The policy is very simple. We're going to start with the simplest case of a deterministic policy where policy maps each state to a single action. So we're going to use this fancy Greek letter pi to denote the policy, and pi of s simply represents the actions selected in each state by the policy. Okay, so in this case, we have pi selecting these actions in these states. And of course, we can also write this as a table. And the thing I want you to note from this is that in some cases, we have multiple actions taken in different states, and sometimes we don't take any of the actions, right? So A2 is just never taken, and that's okay. So that's a deterministic policy, mapping current state to action. This is what the agent is actually doing. Now, sometimes we might behave so that we're not always selecting the same action in every state. In the state, we maybe want to have a distribution over actions in a state. So then we talk about stochastic policies. Okay, so we want a policy to assign probabilities to each action in each state. So now we're going to use the notation pi of A given S. So given the state, what is the distribution over actions? Okay, so this is the stochastic policy. So multiple actions are selected with non-zero probabilities. And pi is going to specify a separate distribution over actions for each state. We're going to have one of these distributions for every state in the world. Okay, so what might that look like? So we have our policy here, and we have state S0. And so most of the time, 60% of the time, we're taking the up action, and we're very, very rarely taking the down action. But each one of them has some non-negligible probability of being selected. And then if we think of another state, this is the same policy, it's just a different state. Maybe we take the up action a little bit less, we take the left action a lot more, but again, it's a distribution over all the different states. So remember, this is a completely distribution for each state. Okay, so that's the two types of policies: deterministic policies, which just map states to actions, and stochastic policies, which is a distribution over actions for each state. And so let's put this into practice, and let's think about what policies might come up here. So let's look at this MDP here. We have a very simple MDP. It's called the butterfly MDP. We have a single state and two actions: go left or go right. If you go left, you go one way. If you go right, you go the other way, and you go back to the same state. Okay, so one simple policy is just, let's just uniform randomly go left and right, okay? So what sequence of actions might we see? We might see left, left, right, left, right, left, right, 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 right. That's totally fine. That's a valid policy. Maybe not super interesting, but it's fine. Now let's think of a policy that alternates by going left and right. So it takes the action that's different than the previous one. So that might look like this, right? Obviously, left, right, left, right, left, right, left, right. We don't want to do this. That's bad. It's bad because I'm going to call it an invalid policy because it's conditioned on something other than the state. It's conditioned on the last action. So it depends on something that's not in the state. So this is where the Markov property comes in. It's saying that the policy should only depend on the current state. And therefore, we get the Markov property. So I don't like to think of this as a limitation on the MDP or the definition of state. I like to think of it as, I don't like to think of it as a limitation on the agent either. This is just a thing that we build into the world where we're trying to find a good state that will make this true. So when we get into function approximation, this will be a little clearer. But you know, in this case, if we really wanted to do this kind of policy, then the last action should also be in the state. And then we would draw the MDP a little bit differently. So just remember that the MDP, the transition dynamics and the policy should depend on the current state and nothing else. If you're depending on a history of things, then you're kind of breaking the rules, and we should reconsider our definition of state. And that's a lot about what reinforced learning is defining our definition of states that's useful for our system. Okay, so we've got deterministic policies, we've got stochastic policies. Now, you know, how do we get these policies? What are we going to use to do learning? We haven't talked at all about learning in MDPs yet. So to do learning, we need to talk about action value functions. Okay, so remember that the goal of life was to maximize discounted sum of future rewards, the return. So this thing is defined in returns way into the future, but we want a data structure that we can use to make decisions right now. So that's exactly what the state action value function is, Q pi of SA. It allows the agent to query the quality of its current situation in terms of future reward. So if we look at this definition, Q pi of SA is the expected return. Okay, so this is just our return equation from before, the future discounted sum of rewards. And it says, if I start in some state S, and then I take the first action A, and then after that I follow pi, we're going to look at the expectation, that's the average return. And so we have this funny notation here, pi and the expectation operator. That's just to say that, this state and this action only help us determine this first reward. And then there are other rewards, so we must have taken more actions, and those are just determined by pi and the dynamics of the world. And what's special about this function is that it really encapsulates the future. So let's just think of what the world looks like to the agent. It's sitting there in state S in red, and there's this tree of possibilities in the future. It takes the first action A, which could lead to a whole bunch of different possible states, but it gets to this particular one. And then from there, it takes another action, which could lead to a whole bunch of other states. And then it gets to this particular one, and so on and so forth. And of course, this tree of possibilities, all of these are possible sometimes. And so we want to compute an average kind of thing through this. There's many places we could end up. Sometimes you get high reward, sometimes you get low reward. And we want to average all those consequences into a single number. Because ultimately, we care about selecting actions. We care about a policy. We care about getting more reward. To get more reward, you have to change what you do. And value functions enable us to judge the quality of different actions in the state so that we can change what the agent does. We can change the policy. Okay, so this is the value function. It encodes all the future and caches it into a data structure that for every state and action, you store this value, and it tells you about the future reward in a state. Okay, so we've got MDPs, deterministic stochastic policies, value functions. Now we want to talk about optimal policies.
Adam, if you like, I think there were quite a few questions on rewards. So would you like to take a moment now just to go back over these? Because I think we had maybe 5 of those.
Sure, can you maybe pick 1 or 2 representative questions?
Yeah, so I think there were at least 2 or 3 questions regarding where the rewards come from and whether we could use curiosity, for example. So Bhargav Patel was talking about curiosity for designing rewards.
Yeah.
And then generally speaking, I think also Davud Kalo was wondering whether there's a risk of maximizing only for short-term rewards. So I think that's the gist of it.
Good. So let's think of the second question first. So the short-term reward thing. This is exactly what this data structure is demanding that we don't do. It's saying we care about rewards all the way into the future. And yes, they're being discounted, but that discount factor gamma tells us how far we look ahead. For instance, if it's 1, we care about the whole future. That could be infinite, but that works in domains where we have finite chunks of experience. But we could make gamma 0.9999999, which means we really care about rewards into the future. So no, there's absolutely no worry about getting stuck on myopic things. That would only happen if gamma was 0, and we'll see that in an example. In terms of where the rewards come from, I love this question because the way I think about it is that reinforcement learning, like when you work in reinforcement learning, you're being very agnostic. You're saying, I don't care where the reward comes from. It's some defined thing outside the agent, and I want to build learning systems that, given almost any reward function, can learn to optimize it. So in some sense, as a researcher, I never worry about this question because I don't ever want my algorithms to only work for certain types of reward functions. But when you come to applications, sometimes the human defines it, sometimes the physical system defines it, right? If you have a robot and it can overheat, then that can be a negative reward. And so you can have a negative reward for overheating, but maybe you care most about the reward, of getting to the charger as fast as possible. So you give, a -1 per step to get to the charger, and you also give a huge negative reward if the agent overheats and you have to walk over and pick it up and put it on the charger. So a lot of times it's human designed. And of course, intrinsic motivation and curiosity, these are brilliant topics. These are things I work on. And that's exactly what we care about when we want our learning system to kind of just learn things about the world like humans do, right? Like babies on the floor, it's not clear what the reward signal is. It looks like they're just trying to learn stuff. And that's exactly what that topic is about, but it's a little bit beyond the scope for today. Okay, so we want to define this notion of optimality because we want to have a clear objective of our learning system. And so we call the optimal policy pi star. And so we're going to define it in terms of our action value function. Okay, so we're going to define an optimal action value function Q of pi star, which is just, you can imagine that for all the states and actions, if you just enumerated all the possible policies and picked the one that got the best action value, then we'll define that as the optimal policy, right? So there's this enumeration game where we have to look at all the possible policies, we have to look at all the state action pairs, and we have to find the one with the largest value. Okay, so this means by definition that all the policies share the same optimal value function because it's part of the definition, which is really, really nice. And we're going to exploit that to build algorithms. And so this is kind of, we get to see the magic of value functions here, because let's just consider somehow some magic oracle like Rich Sutton computed the optimal value function for us. He gave us Q star, right? So that's the value function for the optimal policy. If he gave us Q star, then it's easy to act optimally. We just say in every state, we look at all the possible actions. So maybe you can go up, down, left, and right. And then we look at the Q star value. And then if Rich gave us the Q star value, then we could say, okay, we'll just pick the action that has the biggest Q star value. So this is called being greedy with respect to the value function, or greedification. And this is the primary mechanism that most reinforcement learning algorithms work on. This is the idea behind dynamic programming, which is if you have a value function and you act greedy with respect to it, that's the right thing to do. It'll always improve your policy. And there's this idea called policy improvement that you get into if you read the book or take the MOOC. But this is indeed the technology that we're going to build Q-learning on top of. This idea that if you can learn a value function and then act greedy with respect to it, that'll get better and better and better over time. And eventually it'll converge to optimality, which is really, really nice. So there's been a lot of definitions and concepts, and they're very, very abstract. So I'm from Alberta. I'm an old-fashioned guy, so I'm going to show you a grid world. So you should be able to see this agent bouncing around the world. And what I'm going to do is actually pause it for a second. And so, what are the states in this world? The states are the position of the agent. The agent is this black square. It's where the agent is in this world. So the number of states in this world is equal to the number of grid cells. And the blue ones count as grid cells. The green one counts as grid cells. Everything is a cell in the world, so it's a state. The actions are easy. They're north, south, east, west, or up, down, left, right, whatever way you want to call it. And so the transition dynamics function here is just saying, well, if the agent were where it is right now, if it goes up, it'll go to the square above it. But if it tries to go left, it'll hit the wall, the boundary of the world. If it goes right, it'll hit the other wall, but it can go down. And so the transition dynamics function is describing where the agent can get to in this world. And this world is also deterministic. So that means that given a particular state and action, the outcome is deterministic. So that probability distribution has collapsed into just single outcomes. And so what might the reward be in this world? Well, actually, in this case, we give a +1 when the agent gets to the goal and 0 otherwise. And then there's a gamma of about 0.95. And so what that means is the agent is trying to get to the goal as fast as possible. So I'll let it play again. And so we can see what would the optimal policy be in this world? Well, the optimal policy is literally just find the shortest path to the goal. And so this agent is a particularly good agent. It's using some things that are beyond what we're going to do today, but it's learned a very, very good policy for getting to the goal. And we can see in green what the value function is. So the value function is basically telling us the path to the goal, saying close to the goal, the values are bright green, and then they kind of tail off. And so that's telling the agent in each state, which way it should go. And so here we're only visualizing the value of the best action. And this is an old video from who knows when, and Rich is moving the goal here. And so the agent will go to the old goal, it'll be disappointed, and it'll adapt, and then eventually it'll find the new goal and do better. So that was just to kind of get you to an idea of what states, actions, and rewards might look like. So this is that dreaded sparse reward domain, right? So you only get a reward at the end. This agent in the beginning might wander around randomly and not see the goal for hundreds and hundreds of steps. It only gets a +1 at the very, very end. And so this is one of these memes I'm talking about that people nowadays like to talk about. Reinforcement learning is not good for delayed reward problems. Reinforcement learning is literally designed for delayed reward problems. The guy who invented Q-learning, Watkins, his thesis was called delayed reward problems. Like it's always been the thing that we worry about in reinforcement learning. That is not a new phenomenon. It's a hard problem, yes, it's one of the special features of reinforcement learning, but it's nothing new at all. Here, Luke, how am I doing for time here? What's my end time?
Roughly around 11:30.
I finish at, pardon me?
if we want to leave time for questions, 11.
Okay. So how much time does that give me left? We're in different time zones, so.
About 20 minutes.
15 more minutes.
Okay, I'll go a little bit faster here to leave some time for questions. So I just want to quickly go through this MVP. So we have a state X in this MVP, and then it can lead to different states Y and Z depending on the action you take. So basically, the only decision to make is in state X, where you can go left or you can go right. So you can take action A1 or action A2. Action A1 gives a reward of +1 right away. A2 gives a reward of 0, but then on the way back to X, it gives a +2. And so, there's only two possible policies here, going to A1 and then going to A2. Those are the two possible policies, basically the two paths through this MVP. And so what we want to think about is, how does gamma interact with the optimal policy? So here we're going to make gamma 0. So what does that mean? It means we only care about the first reward we see. So that means the value of policy 1 is +1 because it's just about the first reward. And remember, this is the value in state X. And the value for policy 2 in X is 0 because we only get a 0 in that first transition. We don't see the next one because gamma is canceling out the rest of them in the return. So that means the optimal policy in this case is to pick action A1. It's the first policy. Now, if we make gamma a little bit bigger, we'll see that the numbers change. Now we care about rewards in the future. So if you follow this policy, pi1, you'll get +1, 0, +1, 0, +1, 0, +1, 0. And then you add in all the discount factors with their appropriate powers. You can simplify this expression and you get like 5.3 for the value of that policy. And similarly, if you go the other way, you get 0, then +2, then 0, then +2 over and over and over. You add in all the discounts to the appropriate powers. You can simplify this, and now you get a bigger number. So now we care about the other policy if we're looking further into the future. So to that person's question, it depends on what your gamma is, how far-sighted the agent will be. So we can directly solve MVPs this way. That's exactly what we just did. We took our MVP, we knew there was only two policies, and then we computed the value function for each policy. But that's not a general approach. So even if we just consider deterministic policies, there's an exponential number of policies in a general MVP. And so therefore, we have to enumerate all possible policies, which is an exponential number of them, compute the value function for each one of them, and then figure out what's the best value function. That's not a good idea. So we want to use reinforcement learning methods based on Bellman equations. And that's what we're going to talk about next. Okay? So the first things we've talked about so far are characteristics of the problem. And now I want to get into characteristics of the solution methods. Okay? And there's a little bit of overlap here as there always is. So let's talk about Q-learning. Let's just get right into it. So I want you to pay attention to the structure of this algorithm and don't worry about the update rule. So we have our agent. It has some parameters that control learning, but we won't worry about those. And it has its value function. It's a table of values in Python or in a two-dimensional array, one value for each state action pair. And so we start off in some state, just like the visualization shows on the right. And then for every step, we just do the following. The agent chooses an action according to some policy. In this case, it's going to be some exploratory policy related to the queue, and we're going to get into that. Usually we do epsilon greedy. So in this first state, we pick an action, and then we take that action. And then so the simulator updates, it gives us a new state and a reward. And then we do our learning update. And again, this is the Q learning update. We're going to unpack it in a second, but just it kind of looks like a gradient descent rule, right? You're updating your estimate based on some error term with the learning rate. That's the usual thing. It's just this term is a little bit funny. So, and then we save the state, and then we just do this forever and ever and ever. That's the structure of Q learning. It just continually takes actions and does updates, and hopefully those updates to the value function influence the policy so the behavior gets better and better and better. What's beautiful about this simple strategy is that, someone proved long ago that even without a model of the world, we can get optimal long-term behavior, which is really, really nice. That's what we always want for our learning systems, even if it's under restrictive conditions. So that's Q learning, but let's get into it a little bit more deeply. So let's think of this Q learning algorithm, and let's look at this update rule. So this is like the error term. So like I said, it's kind of like gradient descent. We've got a step size alpha, which is how much we learn, times the error term. And so if it's a usual gradient descent rule, then we have something we're trying to update. And so in the error term, you have a difference between your estimate and some other thing. And the other thing is usually the target of our update, right? So this is a funny, funny target. If you notice, our estimate is actually inside our target. So let's talk about that a little bit. So this is called bootstrapping. This is the key idea in Q-learning, and in fact, all of temporal difference learning. It's probably the main idea of reinforcement learning. And to get there is pretty simple. Let's consider the definition of our state action value function. It's the expected discounted sum of future rewards. Okay. Now that depends on this whole trajectory way into the future, which is a little bit long and messy, and we don't want to wait till the end. You know, that if we had to only learn at the very end of episodes, that would be very, very slow. That's like, you know, you're driving home and a dump truck dumps a load of gravel in front of your car and you don't change how you drive until you get home. We don't want that. So instead, we're going to use a stand-in, a replacement. We're going to use the value function in the next state and the next action as a replacement for all these terms in the rest of the sum. Okay, so we have our equation here, and we're just going to say we want to replace all this stuff with the value function itself. And so this is built on the recursive definition of the return and the recursive definition of the value function. So now we've replaced all these rewards in the future with the value function that we're estimating. Okay, and that's the main trick here, because now if we look at this equation, you know, our estimate in this state and action depends on the reward we get when we take this action, and then it depends on the next state that we end up in, which is given to us by the world, and the action that we would do in that state. So that's only just about one time step of information. We don't have to wait till the end anymore. And that's exactly what Q-learning uses. It uses its own estimate inside its update, and that's what bootstrapping is. It's using a guess to update a guess. And so this is what Q-learning is built on. It's called the Bellman optimality equation, and the same kind of structure can be applied to the optimal value function Q star. And that's why there's a max in there. And so I have a slide about Bellman equations, but it's actually just useful to have this here as notes for you, because I'm gonna give you a copy of the slides if you don't already have them. But I don't want to get into that because I want to get to other stuff. Okay, we're almost there. So we've talked about learning, how learning happens in reinforcement learning systems, but how do we explore? How do we do that thing where we're looking at the different buttons and trying ones even if we think they might be bad? So this is called the Exploration-Exploitation dilemma. You cannot choose the action with the max every time, because your estimates could be wrong. Q pi is an estimate. It changes over time. That could be wrong. So we've got to try all the actions. And in fact, we have to try them an infinite number of times in a finite MVP. And we have to do that in every state. But you can't explore all the time, because otherwise you'd be acting not well at all. You wouldn't be close to optimal. So you have to balance exploring and exploiting. Exploiting means picking what you think is currently the best, and exploring, which is getting more information to update your estimates. So how does Q-learning deal with this problem? Well, Q-learning chooses actions in a way based on Q such that all the actions are taken in all states. That's classic Q-learning. And in fact, most implementations of Q-learning use what we call epsilon greedy. In epsilon greedy, most of the time, so 1 minus epsilon, epsilon is some tiny number, so let's say it's 10%, so 90% of the time, you choose what you think is the best action according to your own estimate. In the state, you look at your action value function, you look at all the possible actions, and you say, I'm going to pick the action that has the highest value according to my own estimate. That's the greedy action. And then some small percentage of the time, like 10% of the time, we just pick a random action. And this guarantees that we try all the actions in all the states an infinite number of times. And it also kind of guarantees that most of the time we're doing what we think is the best thing. And with this, we get convergence to the optimal policy. Now, of course, this is called dithering or undirected exploration. It's a beautiful, exciting topic in reinforcement learning. We call it dithering or undirected because, you just do something random. We might know that one of the actions in this state is really bad. It's like touch the stove. And we tried it a couple times and it burns our hand every time. Epsilon greedy would keep trying it forever in case it gets better. So that's why we call it undirected exploration, because it's really just relying on pure randomness. There are more advanced things you can do. Optimistic initial values is one thing. RMAX, model-based interval estimation, those two require models. But this is a big, big topic in reinforcement learning. And if you'll notice, DQN and Rainbow and a lot of the other big systems, they still do things like epsilon greedy. So this is still a wide open topic. Now, off-policy learning interacts with things in a variety of ways, but the important way is through exploration and behavior. So what is off-policy learning? Well, in a nutshell, it's learning about the value of one policy while following another policy, while using another one to generate the data. And so Q-learning is off-policy because the agent learns the value of the deterministic greedy policy, which eventually becomes the optimal policy, but by following this epsilon greedy policy, which is exploratory. The exploratory policy sometimes takes exploratory actions, so it's not the same policy as the determinants agreed policy. So they're different, and that's what we call off-policy learning. This has all kinds of applications: batch reinforcement learning, learning from demonstration, parallel learning, so hoard and general value functions that Pierre-Luc was talking about, learning models, options, a whole bunch of things. So my last key characteristic of reinforcement learning, and I'm just going to go through a couple quick slides after that, is about non-stationarity, right? That the world is always changing, because that's just the way the world works. And how do we deal with it in Q learning? Very simply. We always update our estimates with the learning rate, so we don't converge to one particular estimate of Q. It can change all the time. And that's really one way that we get adaptivity over time. It's a very, very simple answer, but it's a key part of the formalism. So we never want to stop learning. Learning is never, ever done. And so when you put all these things together, you know, how do we get the first three things? Well, that's NDPs, value functions, and policies. How do we do online incremental learning? That's really dependent on bootstrapping. How do we balance, you know, the need to explore and exploit through randomization and off-policy learning? And how do we handle non-stationarity? Well, we always think about problems as never-ending learning problems. Learning is never, ever done. And so to kind of tile this up, we want to do this with function approximation. You've learned about this in the last 2 days, so this is just going to be apple pie for you. You know, we can't stick things in tables. We can't have a table of values for every state in action. The state space in Go is enormous. It's more than the number of atoms in the known universe. That's ridiculous, right? So we're not going to use tables. We're going to use parameterized value functions. Okay, so we're going to learn a parametric function, and we're going to frame our value learning problem as a supervised learning problem. That means we need to care about generalization and discrimination. So what's an approximate value function? Well, we just had this parameterized version of our Q function. So we're going to use Q hat to denote that it's a parameterized approximation. And so it's going to be dependent on some set of weights, W, which is an Rn, and we're trying to approximate Q star with it, right? So this approximation could be a neural network, and the weights of the neural network are the parameters of the network. Or it could be a simple linear weighting of fixed features. But what's most important is that it scales linearly with the number of parameters, because we're going to need that for scaling. And so how could you integrate this with a neural network? Well, you know, we have our input image here, maybe of the duck. And so, you know, we're going to have the image come in, it's going to pass to the network, and then every node at the end of the network is just an estimate of the value of all the different actions. So the weights at the last layer allow us to learn a unique value for each one of the actions. But you could also do another way. You could, if you wanted to generalize across actions, you could pass the action as input to the system, and then we could just have the output be the estimated Q value for the state and action. And so this means that we're going to have generalization, where we have a fixed parametric approximation. The number of parameters in our approximation, our neural network, is much, much, much smaller than the MVP. So we're going to have to generalize. And what does that mean? Well, it means if the agent is in state 2 and it gets an update, the update is going to affect state 1 and state 4 and maybe some other states. And, you know, this makes sense, right? Like if we have a robot, it's trying to collect hands, it's doing that based on distance sensors. You know, that situation is very similar to, you know, taking a slightly different route to the can, but it takes the same amount of time, so we expect it to have the same value. So we want the system to treat both these situations as the same, even though they're slightly different. That's generalization, right? We want to use updates in one state to learn about other states, because we can't visit all the states because of the number of the atoms in the universe. That's impossible. But we also care about discrimination, right? So sometimes, you know, there's a wall in the way. And so that situation locally to the robot, according to its sensors, might look similar to the situation at the bottom, but they're very, very different. So we need to be able to, you know, share values across states in our value function when they're similar, but discriminate carefully when they're not. And so this ends up being this like 2D space of generalization and discrimination. And so, you know, tabular methods are down here. There's absolutely no discrimination. You can learn a separate value for every state in the table, but with high precision, so it means you have high discrimination. You could also do something kind of stupid, which is you could say, okay, we're going to generalize everything. We're going to learn a single number to represent the value function in all the states. You know, this is like a bias unit. There's literally no discrimination and complete generalization. Now, where we want to be is up here. We want to be able to generalize well and discriminate when we need to. And in practice, you know, our algorithms are going to end up somewhere here, which is not ideal, but, you know, that's where we end up. So, you know, we're going to learn a parametric function for our value function, and then how do we combine this with Q learning? Well, actually, it's really straightforward. It's been around forever, since since the beginning of reinforcement learning. So there's an obvious way to generalize it. It goes back to Watkins in 89. We just have this loss function here. It's the expected squared TD error. The TD error is just that weird target term they were talking about that contains the reward and your value function minus your own estimate. And so if that's your loss function and you work out the gradient descent update rule, it looks something like this, which very much looks like our tabular algorithm. We have the gradient of the network here with respect to our parameters. And the one thing to note here that's worth any mention is that, the computation of this gradient is a little bit of a trick in the sense that we just ignore the contribution of this max Q term here, and that it really does matter. That gradient is not zero, but when we did our derivation, we kind of pretended like it's zero. So it ignores the impact of this first term in the gradient. And what that means is that it's not actually a gradient descent rule. We sometimes call Q-learning a semi-gradient method. And that causes problems. That means that it can lead to instability. So Q-learning can and does diverge. It's not because of control. It's not because of expiration. It's not because of greedification, like taking that max action. And it's not because we're sampling and learning on every time step. And it's not even just because of nonlinear function approximation. It's because, amazingly, dynamic programming methods can diverge with function approximation, which we didn't talk about today. And even TD, just the prediction problem, no control at all, absolutely, like the policy is completely fixed. That can still diverge. So off-policy prediction case. So there's something fundamental about this combination that exists in Q-learning and TD. And we call it the deadly triad. And basically what it is if you're doing function approximation, off-policy learning, and bootstrapping. This is a guy whipping a boot, so I call that bootstrapping. That's the deadly triad. If you have all those things together, you can get divergence. We can't get rid of function approximation, right? We need to scale the large problems. We need to use networks to represent our value functions. And we want to do off-policy learning because it allows us to explore. It allows us to learn about many things in parallel. It's very efficient. So maybe we can get away with not doing bootstrapping. Dale Sherman's is exploring this line of work. I don't want to get away from bootstrapping, but it's definitely something we could do. There are lots and lots of algorithmic approaches to the deadly triad. There's lots of beautiful work, some of it from Doino Prekup's group here. But the story is very nuanced and complex. And that's why I like Hutto's story about it in 2018, which was that, if there's really big differences between the policies, then we can get more divergence. And that's really, really common when we do prioritized replay or sample-based planning or parallel learning. And it happens more with large networks. And we want to do both those things. We want to do prioritized replay. We want to do parallel learning. We want to have big networks. And so if that causes more divergence in DQN, then we need to care about this. And this just represents the tip of the iceberg of the work in this area. So I'm almost done here. So this is kind of like, I was just a little bit negative about divergence problems with Q learning. So I want to be positive and say, look at all these great examples. And there's been beautiful successes in reinforced learning. We were kind of stuck here at around 2006 for a really long time where the best we had was backgammon and helicopters. And the helicopters one is kind of sort of reinforcement learning. But then things really picked momentum and DeepMind has been leading the charge in that. But what I want you to observe from this is that a lot of these things are in simulation. And we care about the real world. And there's good things and bad things about simulations. Simulations are great because we can do research really quickly. We can do very careful scientific studies. We can run things many times and look at parameter sensitivity. That's beautiful. But we can also cheat a bit. We can run on parallel copies of the environment. We can allow the agent to reset to wherever it wants to in the world. We can learn from dying, which humans can't do. We can ignore damage. We can leverage knowledge of the underlying dynamics of the world. I like how Dave Silver puts it. He said all our complex simulators like StarCraft and Atari, they all have a one-step dynamics model underneath. And we know that when we're building our agents, and we're probably exploiting it. And it makes us lose focus of things like data efficiency, parameter sensitivity, exploration. If you can run your agent on 100 copies of the environment in parallel and then run it for 2 weeks on a supercluster, are you really solving the same problem that the baby is when it's playing with toys on the floor? Seems like those are different things. And that's why a lot of things don't transfer from simulators to robots. So we really need to focus on this more. I'm not going to talk about it today, but there are lectures coming up that are going to really focus on that. And we're not done, right? Like this is a table of results with DQN. And this is just highlighting Montezuma's revenge and pitfall. You know, we're getting scores of 0, even though we're superhuman on other ones. And there's even, well, other less known things like tennis. The human best score is 0 in tennis because the tester just didn't figure out how tennis worked. And so we claim superhuman performance in tennis because we get like a score of 1 in tennis, even though we know that that's not good play. So our agents are not superhuman by any means in a lot of domains we care about. And of course, this beautiful work by Joël Pinot's work, just showing that, you know, if we change the network architecture, we get vast differences in performance. If we change the activation functions, big differences in performance. You know, all these little design choices matter, and we don't have the flexibility or the time or the data to do these in real applications. So we're really at the beginning of building intelligent systems, and we should be excited by that and also humble about that. And you know, this is the robot video for Pierre-Luc. I love this video because it's showing, you know, this is Boston Dynamics. They are the best robot company in the world by a large stretch. They have the best robot engineers, the best programmers of robots. And yeah, you guys would not drop the box and fall over backwards when you're trying to solve this task, and most humans wouldn't. And this represents, you know, what we can do with robots. This isn't a learning system, but this just shows the scale and complexity of the problem. They would be using learning if it was more effective than this. And so, you know, everything's wide open for us. And so I just like to finish by, you know, talking about that there's many, many dimensions of reinforced learning. There's problem dimensions, prediction versus control, MDPs, contextual decision processes, contextual bandits, simple bandits. And there's all kinds of dimensions of solution methods, right? Bootstrapping versus Monte Carlo, tabular versus function approximation, on policy versus off policy, model-based versus model-free, you know, all these things. It goes on and on and on. Temporal abstraction, policy gradient methods. And we've just really started, you know, the beginning. We have many of the pieces. We have better and better algorithms all the time. We have bigger and bigger systems all the time. And the theory is always evolving really nicely, but everything is left to be done. And that's exciting. And we should embrace that and be excited because, you know, we get to participate in this exciting future. So with that, I'll show a picture of the reinforced learning groups. This is a picture of, you know, me, Mike Bowling, Martha, Rich Sutton, Patrick Polarski, and a snapshot of our students. I think our group is still bigger now. Reinforced learning is just an exciting place, and I hope you join the effort of doing reinforced learning because we need all the help we can get. So with that, I'm done.
Thank you, Adam. So I think we have time actually to take questions. If I look at the schedule, we had until 11:45, so it means we have 10 more minutes for questions. So I think there are currently 2 people who raised their hands, and I think there are a number of interesting questions in the chat. I flagged a couple of them in the chat, so I think if these people want to ask a question themselves, I think we can do it. But how about we start? Oh, wow, lots of raised hands. I think people were interacting a lot. Adam, I wish you would have seen this at some point. It was just like a fire hose of questions on the chat.
Cool.
Thanks for all your questions. But let's start maybe with Yusra Ibrahim that we haven't heard yet.
Yeah, can you hear me?
Yeah.
Cool. Thank you so much for the call and for the talk. It's very interesting, very clear, very nice introduction. I have a question regarding the non-stationary environment. At which the environment is dynamic. How actually the agent learn in this environment and how it perform. If you can give like a real life example at which it was applied and how the agent actually adapt to these changes in the environment.
Sure. Sounds like a fun question. For some reason, okay. My keynote wanted to tell me about an update. Okay, so I put it back on the Q-learning slide. You can all see that?
Yeah.
Good. Yeah, so I can give a very practical example of non-stationary. So like Pierre-Luc mentioned, we made this robot called the CritterBot, and the CritterBot was this robot that could drive on the floor, and it had an omnidirectional wheel system, which means it could drive in any direction at any time. And to achieve that, you have to have these little rollers on the wheels that allow it to translate in any direction. Very, very fun, interesting action space, but it had a consequence, which was we had to 3D print those wheels, and those wheels were made of a polymer that would warp over time when the robot drove around. And so the consequence of that was, if you gave a certain voltage command, the robot could drive straight. But then as the wheels warped over time, that turned into like a bowed arc. So it wouldn't drive straight anymore, it would drive in an arc. And so if you're learning, say a policy to go to the charger, the learning system can't depend on a specific action making it go straight. It actually has to adapt as the wheels start to warp, and that changes. And so the policy underneath, if the learning system is working properly, should take that into account all the time. Another example would be if my robot learned to dock on like a wood smooth floor, and then I took it to another room with very thick carpet, it would have to adjust its actions to deal with that change. So in one case, the change was the wheels warping, which is just due to the dynamics of the world. That's just a reality of life. And the other non-stationary was due to me actually picking up the robot and putting it somewhere else, like a human intervention. But that's all part of the world. And so how do we deal with this? Well, one way is we deal with it just like I have on the slide here, which is as long as our agent continues to explore forever, and it has this non-decaying learning rate. So, one thing that's common in learning systems when we do gradient descent is we'll do something like ADAM or RMS prop, which makes the learning rates go down as time passes. And in a lot of cases in reinforcement learning, when we have these non-stationary problems, we can't have the learning rate decay, because that means that these estimates will stop changing, the policy will stop changing, and the robot won't learn to adapt to those changes. So this learning rate somehow has to stay at a constant level, or our adaptive learning rate mechanism like ADAM has to be able to pick the learning rate back up when there's changes in the world. And then so the other question is, how do you see those changes? Well, sometimes it can be very hard, because sometimes those changes appear and the robot doesn't even notice it. So that means that we have to have an exploration mechanism here that actually every once in a while tries things out in the world and probes for new things.
Thank you. So I think, how about we go with VD Jane?
Hello.
Hi.
Hi. So I had a question on how do we define the state space representation for the scenarios where we cannot ensure that something is obeys the Markov property?
Yeah, that's a great question, right? So in my simple grid world, the design of the state was obvious. But if we think of just the general scenario, like again, the robot, my CRITIBot robot had distance sensors, it had thermal sensors, it had light sensors. And those give you a snapshot of the world, but they maybe don't capture that there's a graduate student sitting beside where the robot is, and he's going to come and intervene with the robot, or they might not be able to say much about the seasons of the year or things like that. And so, yeah, this question of how you design the state is a very hard one. And it's one we're all struggling with. So the default answer is you have your neural network, and you put all the sensors that you can access into your neural network. And that's one way you can do things, because the neural network with its multiple layers of computation will hopefully extract compositionality and abstract features. But that's assuming that the current sensors tell you everything that's relevant about the world. But sometimes when you do an application, you find out that if I remembered things that happened in the past, my system would do better. And that means there's something missing from your state. And so there's two really primary ways to deal with that. One way is that you do an RNN, right? You do a recurrent learning architecture that uses backprop through time, and you pass it in the sensory information, and then inside the RNN, it'll figure out to remember things from the past if it's relevant inside its state. Now, those things are typically difficult to train, and combining reinforcement learning with RNNs or LCMs is very much early days, and we're still working on it. Another simpler thing you can do if you have an application is you can just feed in that historical information. So, this is what people were doing in the 80s when they were doing robots with reinforcement learning. Like Andy Bartow told me that the first learning system that was combined with a neural network was actually a reinforcement learning system. So this is not new stuff. We've been doing this from the beginning. But what people used to do in the past is, if they had these sensors, they would take exponentially weighted averages of the sensors into the past. So if you have a light sensor, instead of passing into your network the current value of the light sensor, you pass in an exponentially moving average of the light sensor over the past 30 seconds. And now that summarizes the past, and then the neural network can then use that to learn the value function. So sometimes we just pass a history into our neural network. And other times we use like a recurrent learning architecture, like an RNN or an LSTM.
Thank you. I think we're gonna have, maybe we can take one more question. I'd say, how about we go with Sunny Gupta?
Hello, can you hear me?
Yeah.
Yep. So I had two questions. First of all, with the exploration strategy. So I've done some work in bandits. So Thompson sampling seems to be a damn good algorithm. So is there a dithering strategy that's the equivalent of Thompson sampling for MDPs?
Yeah. So you know that in some sense that's one of the big motivations for working in bandits, is that we hope when we study the pure exploration problem in bandits, we can come up with ideas that transfer over. So there's Thompson sampling, there's you know, UCB,
Yeah.
and there are people that work on these. So you know, Thompson sampling is a Bayesian approach, and so there are work on you know, Bayesian reinforcement learning. There's Gaussian process temporal difference learning, where we're trying to actually take into account our estimate of uncertainty to guide action selection. And you know, it goes really far in that you can come up with Bayesian optimal exploration, where you know, if the agent takes its uncertainty and its action selection into account in the right way, it literally is just an optimal exploration strategy. And there's people like Shimon Whiteson that are working on approximations to that. But the thing that we've seen in reinforcement learning is, you know, a lot of the things that we see in the bandit literature, we've tried to transfer them over, and they're difficult because the bandit doesn't have the delay reward problem, doesn't have the non-stationarity, and doesn't have the association with states problem. So like if you consider something like UCB, which is a very popular and hugely effective bandit algorithm, it requires counting, right? You need to count the number of times you've taken an action, and that doesn't work with function approximation. So there's ways to approximate that, but people are doing epsilon greedy because a lot of the ideas don't transfer over easily, and their approximations don't seem to be better than epsilon greedy. Now, of course, this is modulated by the fact that people are using simulators and using basically brute force tons of data to avoid the exploration problem. But yes, there's people working on it. It's very promising, and we need to do more of it. Absolutely.
Okay, thank you. Do you mind if I ask the other question too?
Sure.
Yeah. So about discounting, I still don't understand why it needs to be done. I mean, I get that it makes the total reward finite, but
Yep.
it intuitively doesn't make sense to me that future rewards need to be weighed less than more rewards close to current time. Yeah.
Okay, so imagine I told you right now, if you pick up the glass, I'll give you $100 right now. I'll wire transfer to you.
Yes.
If you do some other thing that maybe is more work for you, I'll give you $1,000 in 100 years. Which action are you going to take?
So should that make a difference for the agent? I mean, the agent shouldn't the agent just care about maximizing its total long-term reward?
Well, so it's a balance, right? And it's a balance controlled by this parameter. So it's a knob that we can tune. It's a problem parameter. It's not fixed to some specific value. We can set it equal to 1. And in fact, we do set it equal to 1 in all kinds of scenarios. So there's no prescription here. Like, this is just a free choice in our design.
So does setting it to 1 not like bring up the making it infinite problem?
Right. So when you set it to 1, it should be a problem where what we say is we have an episodic problem where like a game, you play a game and then it ends and you start again. So that's an episodic problem, and then we can set it to 1 there. In other problems, we can set it really large.
Okay, thank you so much.
No problem.
Thank you, Adam. I think it's 11:45 sharp here in Montreal. So I think I'm going to ask you to post your great question. I believe in Slack would be the appropriate place to post any follow-up questions. I believe that Nadine and the team at CIFAR is also recording the questions. I believe that you've posted in the Q&A. They're all really excellent. I'm sure that Adam would love to take a look at what people have been asking. And also, Adam is going to be available in a breakout session at 4:15 p.m. Montreal time. So I think you can follow up with him. And let's thanks again the speaker virtually. Thank you a lot, Adam, and looking forward to see the cool stuff you're coming up with on your robots. And all right, thank you.
Thank you, Adam. A lot of questions left unanswered. We will see Adam again at 4:15 Montreal time, like Pierre-Luc said. A very short break, and please join us for the panel in about roughly 13 minutes, should I say, at the other Zoom link that you see on your agenda. See you soon. Bye, everyone.